Hyperplane arrangements? Okay, so now the echo. Hyperplanes? Okay, perhaps it works. Okay, so what? No, it's okay. Okay, so what I'm saying is that, so there is this dual picture. Now, we are asking that this reflection belongs to the system, but the last requirement is that there is this number 2 alpha beta over alpha alpha, which belongs, called Cartan integer, but okay, belongs to the integers, okay? This is a very strong requirement, and we're gonna see in generalized root system, we relax it. And then there is the last requirement saying that you don't want a multiple of roots. Now, clearly the fourth statement is like allowing me to do this correspondence, because if you had multiple of roots, then this correspondence is lost, right? One root, one hyperplane. But this is a minor point. We're doing root system, we're not doing hyperplane arrangement, but this is just to tell you that relaxing the last hypothesis is taking us away from here. Now, the non-reduced root system are well known. They've been studied, and I don't comment on them, okay? So if you have seen Lie theory, it's not necessary that you took a full course of it. It's just enough that you glanced at the theory of simple Lie algebras. You know that these 4 requirements that we're given about root system force the rank 2, meaning the dimension 2, to be just one of these 4, right? I write here the A2 system. There is only A1 times A1, A2, the B2, which coincides with the C2 in this case, and the G2, okay? So it's, I mean, I could prove it. It's very simple to show, because you just do some argument on the angles. I just want to point out one small thing about these pictures, which turns out to be important for the generalized root system classification, which is, okay, A1 times A1 is not irreducible, because it's split in 2 root systems, so to speak, of rank 1. The A2, see, does not have any right angle. B2 has 1 right angle, and the G2 has 2 right angles among roots, okay? So it's like these right angles come. I will explain later why. I know you probably never thought about that, and it's like, it's something to think. Okay, now let us see how root systems, so this is the what can I say, the friendly part of the talk. Is all friendly, but this is the friendliest part of the talk. How do root systems come in Lie theory? Certainly, root system comes spontaneously from simple Lie algebras. So you take a Cartan subalgebra, whatever this means. I don't have the, well, perhaps I can say it's a semi-simple element, means diagonalizable, they commute and they're maximal with respect to this property. And then you look at the root space decomposition. This is nothing but eigenvalues, eigenvectors, right? This is a very fancy way to say that. And I put down an example because I think the example explains. So here the trace is 0, so C is the minus A minus B, but that's not so crucial. Now you take diagonal matrices in SL3C, and you take all these matrices and you can diagonalize simultaneously with respect to the adjoint action, because this is a commuting set of endomorphisms, and you get the root space decomposition. So your algebra will decompose in root spaces. And I write the roots alpha. So alpha is a root belongs to H star, the dual. So I have to tell you what is alpha to a diagonal matrix. So it's A minus beta, and this is, sorry, A minus B, and this is B minus C. I don't know, guys. This is like a crash course in Lie theory, is like in 30 seconds. I hope it's more like a review than a true proof, because that would be impossible. But do we get the idea, sort of, what is going on here? You guys mostly know, I hope. You for sure. Right. And this gives me exactly the picture, right? And how do I write the angles? See, because there is the Cartan-Killing form, this is a non-degenerate form that is on the Lie algebra. So the Cartan-Killing of two elements, that is the trace of the adjoint of X, adjoint of Y. I apologize, I didn't write it in the slide. Sometimes the obvious thing escaped me. So this is the non-degenerate form that you have. And then this non-degenerate form establishes duality between Lie algebra and its dual, and then establishes H is identified with H star. And then you have so here you are in H star. Okay. And then you have your non-degenerate bilinear, Euclidean product, and everything is happy. So you have an example. Okay, but I'm sure you know this. Now, Constant proposes a new definition of root system in his paper, and this you may not know. What is the idea of Constant? Idea of Constant is, you know what, instead of doing the diagonalization of a Cartan, which is maximal, abelian, semi-simple, I do diagonalize with respect to a toral subalgebra, okay? So I take not the full diagonal. So for example, in SL3, the full diagonal is this. For example, I can take a toral, which is A, so this is minus A minus B, and this will be minus 2A. Okay, so this is inside. So I diagonalize, of course, this is identified with the dual because we have the Cartan-Killing. So you do a split in eigenspaces. Now, this is a bit different because instead of having one-dimensional root spaces, you have more than one-dimensional. So it's more fun. So Constant develops this theory in a paper which is really called in a very, what can I say, in a very disconcerting way, because the paper is called the Borel-de Siebenthal theorem. And honestly, I know the Borel-de Siebenthal. I don't see it straight connected to this stuff, but the man gives this title. So, and when you draw the roots of this particular constant root system, you see that you don't get nice angles anymore, okay? So this is a root system of SL3, and this is the projected. So you are orthogonally projecting roots from H star to T star. And so the projected root, since you're orthogonally projecting, don't have the nice angles anymore. So they come all crooked, right? And so this definition will not satisfy the root system definition because you don't have the Cartan integers, you know, these reflections, the 2 alpha beta over alpha alpha, they won't be integers anymore. Okay, fine. Constant gives this definition. So it is important to realize that the constant root systems have less symmetries. So I draw this picture to show to you it is a very different picture from this one, because in this picture, you see you are reflecting the root system and the root system continues to, you know, remain invariant. But here, when you try to reflect the root system, you see that it's not invariant, you go somewhere else. So there are no symmetries here, right? So is my claim the Weyl group is an accident is exactly targeted to this point, saying that you do not have all the symmetries that you want. Okay, but let's point out this for constant root systems, and let's go ahead. Are we understanding sort of what is this thing about? Yes, no? Do you guys have questions? Am I going too fast, pressed by the by the late start? Okay. So I'm trying to make you feel guilty, but I know it's not working. I know. That's why I'm making fun. Okay, so, and then there is a third notion of root system. Again, I apologize. There are many other notions. I just report those that seem more significant to me and is a totally personal point of view, of course. So For basic Lie superalgebras, actually, I apologize, should say for, yeah, basic but better contragredient, whatever. But I'm saying that there is this notion of Lie superalgebra, and you can provide a root system for them. It is the same thing. You have something called Cartan subalgebra, except that your algebra is divided in even and odd. If you've never seen this before, don't worry. This talk is not about superalgebras, but I'm just saying that there is yet another definition of root systems, and it's due to Serganova. She defines this root system. She calls them generalized root system, but our root system are generalized root systems. Okay. Okay, so okay, again, I put here in this picture the three type of root systems that we talked about in a very simple example. So there is the example of SL3, which I left on the board, which is perfectly symmetrical. And then the constant root system, which is a projection of an SLN over a two-dimensional subspace. And then there is the SL21, which pictorially looks exactly as SL3, except that I put here the little circles to say that these roots are odd. So there are some symmetries that are forbidden. You can't send an odd root to an even one. So it has less symmetries, okay? So the key difference between these three notions of a root system that are actually employed in Lie theory in a major way is that there are missing symmetries, okay? How do we recover missing symmetries? Serganova defines what is called virtual reflection, and we speak about it now, and she defines Weyl groupoid. We avoid the Weyl groupoid because we don't think we need it, but we look at the virtual reflection, okay? So this is what we do. So what is a virtual reflection? You take a simple root, like this one, and then you do a reflection, you switch, you reverse the alpha string, okay? So look at this, for example, this example is not so smart. So let us look at the reflection, no, because of course it works, but it's not, okay. So let's look at the reflection sigma alpha. So the reflection on this axis orthogonal to alpha. What is this reflection doing? It is switching beta with beta plus alpha. So there is something called the alpha string of a root. The alpha string is this. You have a beta, and then you have a beta plus alpha, and then you have beta plus 2 alpha, and you keep going, right? So this is the alpha string. You sum a root to another one. And you can see experimentally, if you wish, that the reflection are switching the alpha strings. And this example of G2 shows it very clearly, right? So beta, so if you reflect with respect to the alpha root, you switch, you understand, right? What is happening, you switch that. And this is what Serganova does. Now, if you really understand this, you realize that this is a lot of potential because you could do the same when there is no symmetry, right? So this thing has no symmetry, there is no reflection, but you can switch the alpha string. Why not? You can do that. And actually it works. So you create a new symmetry that will not be preserving angles, length, whatever, right? But it's still, it will be a combinatorial, okay? Not an isometry. You can think of it a linear map, though if you want to think it really deep and do for all roots, it won't even be linear, but what do you care? You care what happens into the system. You don't care about the ambient space. Now, Serganova uses these virtual reflections, even defines the Weyl groupoid, I think is also joint work with Pankov, has been greatly influential to us because we thought about our system through that, okay? So far so good. Are we happy? Do we understand? Okay, great. Because now, okay, there is a fun slide to relax. So this is the Calista logo, and now you know why we did the logo that way. You probably knew also before, but it was, I feel so proud about this. I didn't do the logo. I just told the Valeria Montesi, who is an artist, to look at the root systems and produce a logo, and she did this beautiful thing. And Marianne Yedo, of course. Me, I'm no artist. Okay, finally, the generalized root system. That's great. So let's look at them. So what is a generalized root system? You want a Euclidean space, so you have a non-degenerate positive definite form, and you want to play this little game. Whenever there is a obtuse angle, the sum is a root. Whenever there is an acute angle, the difference is a root. Very simple, right? Okay. And at this point inside of you, you may think, wait a moment, Fioresi, what are you talking about? In superalgebras, there is no such thing as a positive that product, but be with me, we will find it, okay? So all the examples that we saw just a little while ago, they're all examples of this, though to prove it, it takes some time, but we will get there. So if you look at these examples, these are all examples of roots system in this generalized way. But if you look, for example, at this is not a root system, right? Because this is, and you don't have this root, okay? So this is not an example of generalized root system. Just to tell you what is example, what is not. Okay, and if you know Lie theory, you know that all root systems in Lie theory satisfy these three properties. Okay, so this is our definition. Perhaps I should write it here in a little corner because we're going to see this. And so if it is positive, implies that alpha plus beta is a root. If it is negative, the difference is a root. No, it's the other way around. Get confused. And then if it is 0, then alpha plus beta is a root, if and only if alpha minus beta is a root. Okay, this is mine. All right, so this is the definition we play with, very simple. And okay, I really like the Occam razor, right? That Sean said yesterday. If there is something simple, that is probably the best thing to do, right? That is what we think. Okay, so again, I try to write what are, at the moment, we don't know why they are, but root system of semi-simple algebra, yes, they are root system, the constant root system of contragredient, Lie superalgebra are examples, not obvious now, not obvious at all. The so-called crystallographic hyperplane arrangements are examples, a special case. And what is called the TITS hyperplane arrangements is Wey's private communication. He wrote to us after we posted and said, oh, I'm doing that also. I'm like, okay, but if you don't post it on the archive, how are we supposed to give you credit? But okay, we will give him. He's actually doing exactly the same. And then the fascinating thing is that Alexevsky, in his work on flag manifolds, the complex structures of flags are indeed ruled by this type of root systems. And if you think about it, when you look at the Levy is a centralizer of a toral subalgebra, right? And that's the thing that's coming out. So this theory is capturing complex structures, but I didn't want to get too much into this. Okay, and then I just wanted to get a feeling of what are these strange objects about. Okay, the first example, one may say, okay, in this definition, there is no requirement that a multiple of a root is a root or not. So you may ask yourself, what if you add the reduced condition? So if you only want multiples of roots. And then you find that you get the very similar to A2, a two-parameter family, is this drawing that perhaps I have it of the crooked A2, and also crooked B2 you can have. But notice that the more you get into this, so you have a 2-parameter family of the A type and 1-parameter family of the B type, but you have just one G2, because G2 is rigid. It has 2 orthogonal angles, and you can't really have infinite family. So let me, yeah. So this is the 2-parameter family of a 2, because essentially what you play, you have length and angle to play with. Okay, you can define matrix, you can define linking diagrams. What we discover is that these objects are not so useful beyond rank 2, because the problem is that in rank 2 reduced are very small, but the moment the complexity raises, these angles will not tell you the system. There is more. So it's, I'm trying to show to you the complexity. So these are the reduced ones. How about the non-reduced? How many multiples of roots can you have? So these are examples. I will go fast. So this is a B type. You see that you can have the usual B2, or you can have this B2 where the lengths are not, you know, that they're not what you expect. Okay. And then I just wanted to get you a feeling that in rank 2, if you relax the hypothesis of a multiple of roots, you can have this very exotic generalized root system. And if you try to verify the axioms, it takes a while, but this is generalized. And I put it there, then I will show you again a slide in the classification, because actually this is the highest, 4. You cannot have a 5 alpha, 4. That's I will, and this actually somehow resonate because, okay, it's still early. Let me go ahead because it's a mystery. Okay, if you have a generalized root system, you can define a positive system. Now, if you don't know Lie theory, that's going to be a problem because, but if you do know Lie theory, you know exactly what a positive system is that you can find, get an hyperplane, and then you get the positive part of the hyperplane, the negative part, and whatever is in the positive part is called positive. And it turns out that in Lie theory, for root systems, all roots are integral positive or negative combination of bases. And this is the truth here too. So this puts contact with the so-called crystallographic hyperplane arrangement. So you can define a root positive system, and you have that every positive system admits a base. And then I also wanted to say that R may look different, we choose different bases. I don't have the time. I wanted to do a little calculation, but we don't have. Every positive system has a highest root and lies on the side of a hyperplane. If you know root system for Lie algebras, this is really what you expect. This is what happens, right? Same. So the proof is not complicated at all. Okay, then you can define height of a root. And I just wanted to spend one moment on this, saying that since Stefan so much talked about the pose sets, now so the root system is a pose set where you define the height of a root simply as the number. So for example, here for A2, here the pose set is you have alpha, and you have beta, and then you have alpha plus beta. Is a very boring pose set, right? The height is 1 here, and then the height is 2, 1 plus 1, right? And the more is complicated, the more. Now, it turns out that this is a lattice. So you have a join and you have a meet. Perhaps I'm asking the audience, perhaps this is a property that is known for Lie algebra root systems. We couldn't find it anywhere. So we prove it for generalized, and then we get it for root systems too. So there is there is this property, and one has to be careful because one may be tempted. See, if you get the join, you take the minimum of AI and BI for 2 roots, and you think, oh, you know what? For the meet, I do the same. I get the max. Oh, sorry, I forgot an A alpha here. But the max will not work because if you have I show you, because if you have this a little more complicated root system, right? Is what? Is nowhere, yes, because it's a bit complicated. No, I think it's join. Ah, perhaps max. Height. Okay, let me see. Did I make a mistake? Huh? No, but it is join and meet. It's different, right?
The root is higher, as bigger are the coefficients. So to reach the join, you should...
Oh, you're right, the max. No, you are correct. I'm sorry. This was an error of switching max with min. No, but despite Fabio catching me, what I'm trying to say is that if you take here, for example, so here you don't have alpha plus gamma, so this is not a root. So if you try to get the min, you will be... So I'm trying to say there is some care to exert in doing this game, but evidently I didn't put care in defining this, so I cannot further comment. Okay, but let me put down the most important thing. So if you have a root system in this generalized way, you can look at subsystems. This you can do also in Lie theory. I mean, for root systems, you look just an hyperplane and you look what is there, or sorry, a subspace and what is there. But what you can do, which is really important here, you can take quotients, okay? And that's really the fun part of it, because a quotient of a root system, it's not a root system, but the quotient of a generalized root system is a root system. So if you have a root system and you take the quotient, this is not a root system. But if you have a generalized root system and you do the quotient, this is a generalized root system. And that's what motivated us, because the constant root system are quotients of Lie algebra root systems. And so you have this factorial property. I on purpose did not speak about groupoids, functors, and category, because I didn't want to I didn't want to give extra burden to this. It's not needed to have a understanding, but it's very important. If you have a root system, the quotient, so generalized, is a root system. Okay, so this is a very, very important thing. Okay, perhaps I skip the quotient example because I don't have the time. Okay, so if I have a generalized root system, I can give two notions of isomorphism. So I can ask that there is an isometry between the two root systems, or I can simply ask there is a vector space isomorphism, right? So essentially, I can decide that my Euclidean product to be preserved or not. Clearly, in this example, you get equivalent root systems that are not isomorphic because the roots are not, the length are not preserved. And then you can ask, can I classify these things up to isomorphism, up to equivalence? So this is a question you may ask, but the other question is like everything we've seen so far. Is it really an example of a generalized root system? In what sense? So this is the, so these are our main results for this first part, that the quotients of generalized root system are indeed generalized root systems. This tells me immediately as a corollary that all constant root systems with respect to a toral subalgebra are generalized root systems. So this will open to deal with the complex structures of flags and super flags, by the way, because there are super constant root systems also. And you can really deal with bases and play with them very easily with this notion. And then we also have that all root system of contragredient superalgebra are generalized root systems. Now, this is a bit tricky, right? Because if you look at contragredient superalgebras, there is a God-given product, which is this one, which is invariant. Yes, which is invariant. But this is not the product you look at. You look at a different product, which is not invariant. So I know you lose something. What can I say? But it's very effective. So all the examples we've seen so far are indeed generalized root system and are very fundamental objects in mathematics for geometry. Not only this, but we discovered that also Lie algebras are quotient of Lie algebras. It's kind of fun, right? So if you look at the B, C, F, and G2, so these are all quotient of the simply laced. What are simply laced are those for which the length of root is all equal. So this is an interesting result saying that even in the theory of Lie algebra, you can realize this B, C, F, and G as quotient of simply laced. And I just want to say that this is not diagram folding. If you know what diagram folding is, great. If you don't, it's okay. But I'm saying it's something more than that. And then we can provide a table that gives all these quotients. Dimitrov is very, very thorough in these calculations. I am at what he can do. I am not a calculating person. And then I just finish by saying that we also have a theorem of classification, though I'm not so hot in classification because I've not been driven by the classification. So let me tell you this really straight. This theory I don't do for classification. I do to get a fundamental conceptual understanding of root systems. But then for fun, we classified the root system of rank 2, and these results actually recover all root systems with rank 2 complex structure on flags, G mod P. They were studied by Graev in 2015, but one important point, Graev looks at the semi-simple group divided parabolic. We don't assume, and yet we recover all these systems. And one more slide, just pictures to have you feeling how they look like. So this is the quadruple root, and this is the triple root. So this is, we have one system with quadruple root and 4 systems with triple roots, and I think 8 with a double and so on. So thank you very much for your attention. I was good. I stayed in the time. No, there is a Weyl groupoid. You can recover Weyl groupoid, but Weyl group is impossible because there is no symmetry, right? Yeah. No. We think that's not the right way to look at it. We think Weyl group is really an accident. And if you want to look generalized, I know it's very provocatory statement. I understand. We really all like a Weyl group, and especially I personally like a lot Weyl, right? But that's not the right object. That's how we feel. No, it's really forget about the group. That's all I'm saying. Yeah. Sorry. I don't understand the question. When you take the quotient, no, you go different. You go down dimension. It's really a quotient. So the roots, I'm sorry I didn't express this clearly. So you start from vector space V, and you get, say, R, and then you take the quotient, you are going V mod something. So it is like a quotient of the, you go down dimension. Yeah. I do. And then the quotient will generate the quotient. Yeah. Okay. Sorry for not being clear. Yes. Yes. No, it's right that you're taking revenge. I understand. Go, Andrei. No, I really like your question. No, let me answer. So in this talk, I don't speak about classification, but we do wonder about classification. So we classify rank 2 systems, and you may ask, what is else, right? So first of all, our conjecture is that all generalized root systems are quotient of Lie algebra systems. Okay, this is our conjecture. And I think that if you ask me in 2 weeks, we're going to have this as a theorem. That so this fully classifies them, right? Yes. Is it a Lie algebra? You tell me. No, I have an answer. If our conjecture is correct, that really they come quotient of Lie algebras, then they will be representing complex structures of flags. There will be a one-to-one correspondence with them, either flags or super flags. So there'll be all of them. But at this moment, I confess my inadequacy. We don't have this theorem. But I think we're almost there. It's like 2 weeks, 1 month. I don't know. Okay.
So in the classical theory of systems, one of the main ingredients in order to classify is thinking.
Yes, very good question. I didn't have the time to express.
Let's say bilinear forms are not
very intelligent question. So if you think about thinking, what does thinking tell you? Tells you that the rank 2 rule everything, right? Because you move with the rank 2, right? Here, no, for sure. But what we think in the classification, this is actual work by Lentner and Kuntz, is that you need a simplex. So not just the line, you need to consider simplex of thinking. That may recover. So we are thinking about that, but this is an excellent question. I didn't comment. Thinking will not give you everything for sure. You need to go beyond one dimension, simplex, 2, and so on. Yes. You guys like it? I am sorry. Te devi dire sì per forza.